Welcome to the deep dive. We've got a stack of sources here detailing, well, a really insidious problem inside industrial plants. Corrosion from ammonium chloride and amine hydrochloride salts.
Yeah, it's a fascinating and frankly pretty dangerous mechanism. We're not talking about slow general thinning here.
No.
This is localized, it's fast, and it can cause major failures, sometimes surprisingly quickly.
So our mission today is to dig into this source material you sent over. We want to pull out the practical knowledge, right? What causes it? Where does it hit hardest? And crucially, how do people manage it?
Exactly. We need clarity on the mechanism, the vulnerable spots, and the tools to fight back. Protect the equipment.
Okay, so let's start right there. We often think of corrosion as, widespread metal loss. But you're saying this is different. What's the core definition here?
It's primarily localized corrosion. Think pitting, little pinholes that go deep, fast. And it happens right underneath where these salts deposit. And here's the bit that often trips people up. The sources emphasize this can happen without a free water phase being obvious. The salt deposit itself is the starting point.
Right, that's the first hurdle, because usually we're laser focused on the water dew point, aren't we? So let's get into the science. What conditions need to line up for this specific type of corrosion to kick off?
Okay, so you need the building blocks first. That means enough ammonia, NH3, and hydrochloric acid, HCl. Or sometimes it involves amines.
Right, the neutralizing amines people inject.
Yeah, those can form problematic salts too.
Yeah.
So you need those chemicals. Then you need temperature, the right temperature range.
Yeah.
And you need water, even if it's just a tiny amount locally.
Okay, temperature. This is where the sources really threw me. They talk about high temperature salting. That sounds completely backwards.
It does seem counterintuitive, doesn't it? But what happens is you have these hot vapor streams carrying the HCl and NH3. As they cool down, before they hit the water dew point, the gases react.
And form solid salt?
Exactly. Solid ammonium chloride, NH4Cl, just precipitates, like snow, directly onto the metal surfaces. That's the salting. And it happens well above where you'd expect water to condense out.
How far above? What sort of temperatures are we talking about?
The material points to salting observed up to around 400 degrees Fahrenheit. That's, 205 Celsius?
Wow, 205 C. That completely changes the game for material selection and monitoring in those zones, doesn't it?
Absolutely. Because your standard high-temp alloys might resist dry gas, but suddenly they've got this corrosive salt patch stuck to them.
Okay, so the salt forms even without bulk water.
Yeah.
But then why is the presence of any water so critical? Why does it make the corrosion rate just skyrocket?
Right, because these salts are incredibly hygroscopic.
Meaning they attract water.
Yeah, strongly. They act like little magnets for water molecules, pulling moisture right out of the surrounding vapor stream, even if it's technically dry.
Ah, okay.
And when the salt absorbs that water, it dissolves and hydrolyzes. Basically, it reacts with water.
And
It forms a very concentrated, highly acidic solution, but it's trapped right there under the salt deposit against the metal.
got it. So the deposit isn't just inert, it becomes this tiny self-contained acid bath.
Precisely. And that combination, localized concentrated acid, is what drives these incredibly high corrosion rates. The sources mention figures like over 100 millimeters.
For 2.5 millimeters a year.
Yeah, in a localized spot. That can punch through a pipe wall really, really fast. Huge safety risk, huge economic risk.
And you mentioned the amines earlier. It's not just ammonium chloride. If you're adding neutralizing amines to fight HCl.
They can react with the HCl too, forming amine hydrochloride salts.
Yeah.
And the sources are clear. Those salts behave pretty much the same way. Hygroscopic, form nasty acids when wet.
So fixing one problem potentially creates a similar one.
It's a balancing act.
Ooh.
Now, visually, if you actually see these deposits, they're described as whitish, sometimes greenish or brownish powders or crystals.
But the real signature is underneath.
That's the key. Underneath, you find that characteristic, very localized pitting damage. That's the calling card of this mechanism.
Okay, now we have a picture of the chemistry, how aggressive it is. Where does this typically show up in a plant? Which pieces of equipment are most vulnerable to these salts condensing and causing trouble?
The sources point consistently to areas where hot process vapors are cooling down or slowing down. That's where the salts have a chance to form and drop out.
Makes sense. So give us the hit list. Where should people be most vigilant?
Top of the list, definitely crude tower overheads. That means the very top of the tower, the top trays, the overhead pipes, the first exchangers.
Especially low flow areas in those exchangers.
Exactly. Stagnant zones are bad news. That whole overhead system is prime territory because you often have both HCl and ammonia present after the desalter.
Okay, where else?
Then you look at hydroprocessing units, hydrotreaters, hydrocrackers. specifically the reactor effluent streams. Same for catalytic reforming units. Their reactor effluents in the hydrogen recycle system can be susceptible. And finally, FCC units and delayed coker fractionator overheads. Again, it's those overhead systems, top pump-arounds areas where vapors are cooling and salts can deposit.
That's a lot of critical equipment across a typical refinery or petrochemical plant.
It really is.
Given how nasty this corrosion is, I imagine material selection is a nightmare. The sources say pretty much everything is susceptible, but
Yeah.
there must be a hierarchy, right? What holds up best?
There is a hierarchy, yeah, but best is relative here. Starting from the most common, least resistant materials. Number one is carbon steel and your basic low-alloy steels. They suffer quickly.
Standard workhorses.
Right. Then you get a noticeable improvement with the 300 series stainless steels. Step up again, you've got duplex stainless steels and things like alloy 400, alloy 800, 825 more specialized nickel alloys.
Getting more expensive now.
Definitely. Then for even better pitting resistance, you're looking at the high molybdenum nickel alloys. Think alloy 625, alloy C276.
Okay.
And at the very top of the resistance chart, specifically for this type of attack, sits titanium.
But, and this seems critical, the sources warn that even these top-tier alloys aren't foolproof, right? If I've shelled out for alloy C276, am I safe?
That's the crucial caveat. You're more resistant, significantly so, but not immune. This mechanism is so localized, and the environment under the deposit is so aggressive.
Like a super concentrated acid.
Exactly. It can overwhelm the passive layer of even these really good alloys. The sources explicitly state that even alloys 625, C276, and titanium can still experience pitting corrosion under these salt deposits.
So metallurgy helps, maybe slows it down, but it doesn't eliminate the risk.
Correct. Which tells you that mitigation, preventing the deposit or removing them, has to be your primary focus. You can't just engineer your way out of it with fancy metal alone.
That sets us up perfectly for the next section. If materials aren't a silver bullet, how do we actively fight this? Let's start with prevention, stopping the salts from forming in the first place. How do we limit the ingredients, the HCl and ammonia?
It really boils down to good upstream control. In crude units, the number one thing is effective desalting. Get the chlorides out of the crude oil before it hits the distillation tower.
And sometimes caustic injection.
Yes. Adding caustic soda to the desalted crude can help neutralize any remaining HCl precursor chlorides. For hydroprocessing units, you need to watch the chlorides in the hydrocarbon feed and in the makeup hydrogen gas. Both can be sources.
Hydrogen can carry chlorides.
Oh yes, depending on how it's produced and purified. It's a known pathway.
Yeah, okay. And for cat reformers, they make hydrogen, so.
Right, for reformers, a key strategy is treating the net hydrogen product gas. They often use alumina bed chloride traps, basically, absorbent beds that pull the chlorides out of the hydrogen stream before it gets recycled or sent elsewhere. Stops the problem from circulating.
Okay, so that's limiting the formation. But we know deposition can still happen, especially that high-temperature salting above 200 C. So active management becomes key. The sources hammer on one technique again and again. Water washing.
Water washing is the primary tool for dealing with deposits once they form, or preventing them in some cases.
Now, there seems to be a big operational difference between continuous washing and intermittent washing. Why is continuous often preferred?
Yeah, this is really important operationally. Continuous water wash injects a small stream of water all the time. The goal is to keep surfaces wet enough to dissolve any salts as they form, or just wash them away before they can stick and build up.
Keeps things clean constantly.
Ideally, yes. Especially critical in exchangers to maintain heat transfer. Intermittent washing is different. You let the salts deposit for a while.
Which they will, especially above the dew point.
Right. And then you periodically hit the system with a larger volume of water to dissolve and flush out the accumulated deposits. But doing this, particularly in big columns like FCC or coker fractionators,
Requires slumping the column. What does that mean?
it means you often have to significantly disrupt normal operation. You might need to reduce feed rate, change temperatures, sometimes reroute intermediate product streams back into the wash zone just to get enough liquid flow to dissolve heavy salt buildup on trays or packing.
Sounds disruptive and costly.
It absolutely can be. Lost production, operational headaches. That's why for those big, high-throughput units, continuous water wash is pretty much standard practice. They just can't afford the disruption of intermittent slumping.
Okay. What about inhibitors? We mentioned neutralizing amines earlier, but what about filming amines? Do they help here?
They're often added, yes. Filming amines are designed to coat the metal surface with a protective layer. The problem is, if you already have a solid salt deposit,
The inhibitor can't get underneath.
exactly, the salt deposit acts like a physical barrier. The inhibitor might flow right over the top, but the metal surface under the deposit remains unprotected and exposed to that nasty concentrated acid environment we talked about. So they can help on clean surfaces, but they don't solve the problem once deposits are established.
Makes sense. Okay, final challenge. Inspection. If this damage is so localized, tiny pits, finding them must be like finding a needle in a haystack, especially in huge exchangers or long pipe runs.
It's incredibly difficult. That's one of the biggest challenges. And the salts aren't always stationary, remember? They can wash downstream, so the place you find corrosion might not be where the salt first deposited.
So standard inspection, like taking a few random ultrasonic thickness UT spots.
Generally not very effective for this mechanism. You can measure hundreds of points and completely miss the one deep pit that's about to cause a failure. It's just too localized.
So what you need? What are the preferred monitoring techniques?
You need methods that give you much better coverage. Scanning techniques are key. For measuring wall thickness, things like automated UT, AUT, or doing manual UT but on a very tight grid pattern.
Close grid scanning.
Right. Get high-density data. Guided wave testing, GWT, is also mentioned as a useful screening tool. You can quickly scan long lengths of pipe to find areas suggesting wall loss. Then you follow up with detailed scanning in those spots.
And inside tubes, like in air coolers or shell and tube exchangers, which are definitely prime locations.
Yeah, for tubes, you need specialized tools. Things like IRIS internal rotary inspection system, magnetic flux leakage, MFL, remote field testing, RFT, near field testing, NFT. These work well for carbon steel tubes.
And for stainless or other non-magnetic tubes.
For those, you'd typically use eddy current testing. ECT or IRIS can work there too. The point is, you need techniques designed for full volumetric or full surface inspection of the tubes. You have to look everywhere.
You're hunting for that one critical flaw.
You are. And one last monitoring point, linking back to mitigation.
The water wash system itself.
Absolutely critical.
Yeah.
If water washing is your main defense, you have to make sure it's working properly. That means routinely checking the injection points, the flow meters to ensure correct rates, and especially the spray nozzles.
Why the nozzle specifically?
Because if a nozzle is plugged or damaged, its spray pattern gets distorted. It might be missing a whole section of the tower internals or a part of the exchanger tube sheet. That creates a dry spot where salts can build up, even with the wash system running. So nozzle condition and spray pattern are non-negotiable checks.
Okay, this has been a really insightful deep dive. It feels like fighting this ammonium chloride corrosion isn't about finding one magic solution, is it? It's more about constant vigilance and really tight operational control.
That sums it up well.
So let's recap the big takeaways. First, this stuff is nasty, highly localized pitting, super aggressive, and critically, it can start forming as solid salt well above 200 degrees C, which is not intuitive.
Definitely. Second, it impacts a huge range of essential equipment. Crude overheads, hydrotreaters, reformers, FCCs, cookers, and even your best alloys, your 625s, your titaniums, aren't totally immune to the pitting.
Right. And third, managing it relies heavily on preventing the chlorides and ammonia getting in, using continuous water wash effectively to flush away any deposits, and backing that up with specialized full coverage inspection because the damage is so hard to find.
That's the core strategy. And it's important for you, the listener, to see this isn't happening in a vacuum. The sources link this mechanism to other related threats.
Ah, good point. What else is nearby, chemically speaking?
Well, it's closely related to general hydrochloric acid, HCl corrosion, obviously. Also, chloride stress corrosion cracking ClSCC, which is another huge issue, especially for stainless steels. Then there's aqueous organic acid corrosion, sometimes found in overheads too, and concentration cell corrosion in general.
All driven by chlorides, acids, water, getting concentrated in problematic spots.
Pretty much. They're all part of the same family of wet, acidic, chloride-driven corrosion mechanisms that plague these units.
So the final thought for you to chew on is just how complex this specific threat is. You're dealing with something corrosive that forms solids at high temperatures, can move around the system, hides in hard-to-reach places, and causes tiny localized damage that requires advanced scanning to even detect.
It demands constant diligence. Missing one deposit, one plugged wash nozzle, or one deep pit during inspection can have really severe consequences. You have to assume it's there and proactively manage it.